In this video, we discuss learning outcome number 5 from lesson 10.1, which is about conducting a hypothesis test to determine whether there's a linear correlation between variables using the p-value method. Now, the null and alternative hypotheses for claims about correlation are exactly the same for the p-value method as they were for the critical value method. So remember, rho is the linear correlation coefficient of the population. Our null hypothesis is always in this book, in this class, that the linear correlation coefficient for the population is 0. So that's saying that there is no correlation between the two variables. Now, if we are saying there is a correlation between the two variables, that's the same as saying that rho is not equal to 0. So we have some non-zero correlation between the two variables. Now, very rarely, we may want to say that we have evidence of a positive correlation. So that's saying that as one variable goes up, the other one goes up. So in that case, our alternative hypothesis would be that rho is positive. Another possibility is that we might say that, or we may wish to say that we have a negative correlation between two variables, which is to say that rho is a negative number. So we could use one of these alternative hypotheses, which would turn our hypothesis test into a right-tailed test or a left-tailed test respectively instead of a two-tailed test. But for the most part, we're just looking for evidence of a correlation. So we're going to stick to this null and alternative hypothesis right here. Now, the requirements for testing a claim of linear correlation between two variables are exactly the same as they were for the critical value method as well. We need our pair or sample of paired data, to be a simple random sample, and we have to have quantitative data. And then our second requirement is that when we look at that scatter plot, we need to see that the data approximate a straight line pattern. And lastly, we need to look at that scatter plot and see if there are any outliers. And if there are outliers that are known to be errors, we should remove those. And if there are outliers that may not be errors, we should compute R with and without the outliers and consider those two values of R, or for those multiple values of R when we're doing our analysis. Now, the second and third requirements are being used to verify that the XY pairs have a bivariate normal distribution. That just means that when one of the variables is held constant, the other variable has a normal distribution. That is pretty difficult to check in practice. So rather than checking that, we're checking these two requirements, requirement number 2 and requirement number 3. If requirements 2 and 3 are met, then we can assume that the XY data have a bivariate normal distribution. Now, when we're using the p-value method, sometimes we use technology and it immediately gives us the p-value. Sometimes we need to compute the p-value by finding the corresponding test statistic. So we're going to find a test statistic t. Now, that test statistic t is related to the distribution of the sample statistic r. Remember, r is computed using sample data, so that makes it a sample statistic. And that means if we had a bunch of samples of the same size, we could compute the sample statistic r for all of those possible samples of the same size and then look at the distribution of R. Well, when the true population linear correlation coefficient is of low value, the distribution of the sample statistic R is approximately normal. But when the population parameter rho, that's the linear correlation coefficient for the population, is high, that distribution of the sample statistic R tends to be skewed. But we can find an approximate value of our test statistic t using the formula below. This is a test statistic t from a student t distribution that corresponds to our sample statistic r. T is given by our r value that's computed from our sample data divided by the square root of 1 minus r squared divided by the sample size minus 2. This comes from a student t distribution with n minus 2 degrees of freedom. Then once we have that t-score, we can find the p-value using this test statistic. for a two-tailed test, which is what we have when we're looking for evidence of a correlation, the p-value is the area and the nearest tail from that test statistic doubled. So we can use t.dist t.2t, that function in Excel, or we can find the area and the nearest tail using that t.dist function if we're interested in area to the left, or t.dist.rt function if we're interested in area to the right. And then once we find one of those, we can just double it in order to find our p-value. Then once we have our p-value, we use it in the same way that we used it whenever we were talking about hypothesis tests in chapters 8 and 9. If the p is low, we say that the null must go. Now remember, the null hypothesis tells us that there's no correlation. So if p is low, that's saying that there is evidence of a correlation, a linear correlation between the two variables. Now, if p is high relative to alpha, then we're going to fail to reject the null. So what we're saying in that case is that there may, or there is not enough evidence to reject the possibility that there's no correlation between the two variables. There may be a linear correlation, but we don't have enough evidence to support that yet. So if p is high, we say, the null can fly. We fail to reject the null. That means we do not support the claim of a linear correlation. And of course, after all of that, you want to state your final answer in terms of the original hypothesis, which is that there's a linear correlation between this variable x and this variable y, and x and y actually have some meaning. So let's look at an example. We're going to revisit that same data set from before. This time we're going to use the hypothesis test, using the p-value method. We're still using that 23, or those 23 pairs of chocolate and Nobel laureate data to conduct a formal hypothesis test of the claim that there is a correlation between the amount of chocolate consumed in a country and the amount of Nobel Prizes awarded to people in that country. We're going to use a 0.05 significance level, and we'll use the p-value method this time. So here's our data. I actually have this in an Excel spreadsheet. Now, before we do anything else, we should verify that the requirements are satisfied. So we need to think about whether we have a simple random sample of quantitative data. Now, this one is actually questionable. We've got 23 data points, so that's data from 23 countries. But there's no reason that we should believe that that is a simple random sample of 23 countries from around the world. Since this may not be a simple random sample, the results that we obtain through the rest of our analysis may not be valid. We can temporarily assume that we have a simple random sample, but just keep this in mind that if it's not a simple random sample, then everything that we do after this point is questionable. Now, to check the second and third requirements, we need to look at a scatter plot. We see that we have approximately a straight line pattern. It looks like there's a positive correlation there. A line that would fit through this data would have a positive slope. And it doesn't seem that we have any outliers, so we don't have to worry about that either. Okay, so there may be a positive linear correlation. In order to determine whether there actually is evidence supporting that claim of a positive linear correlation, we need to compute the R value, and then we're going to use the R value to compute the corresponding test statistic, and then we'll use the test statistic to compute the corresponding p-value. So in order to do all of that, we need to identify our sample size. Our sample size is 23. We've got 23 ordered pairs, and then we'll compute R using Excel. So let me show you how to do that. In Excel, I type equals PEARSON, open parentheses, and then you want to type your first array. I just select that first array, drag and drop, comma, then select your second array. You want to drag and drop there as well. Close parentheses and hit enter, and that's your R value. Oops, that's not what I intended to do. We want to round to 3 decimal places. We get that value. I don't know why I accidentally tapped over, but that's our R value. Then our test statistic comes from using this formula. The test statistic t is r divided by the square root of 1 minus r squared divided by n minus 2, where n is the sample size. When I did this calculation, I got a 6.100 approximately. Let's do that in Excel now. So we'll type equals, then we'll choose the r value. We'll divide by the square root of open parentheses for the numerator. We want 1 minus r squared. Close parentheses. And then we're dividing by the sample size minus 2. We had 23 ordered pairs. Sample size minus 2 is 21. Close parentheses. And we get this value. If I'm rounding to 3 decimal places, I've got 6.100, which is exactly what we see on the slide. Now the next thing we want is to find the area beyond that test statistic for our p-value. Since we are dealing with a two-tailed test, I would use t.dist.2t. Then I enter my test statistic and the number of degrees of freedom, which is the sample size minus 2. And the p-value turns out to be this very small number of 0.000000472 approximately. Let me show you how I find that in Excel. So my p-value is this, t.dist.2t, open parentheses, select the test statistic, and then type in the number of degrees of freedom, close parentheses, and you get that 4.7169 times 10 to the negative 6, which is the same as that value that I gave you on the slide. Oh, it's not actually showing that 10 to the negative 6. That's okay. I guess it's listing it in scientific notation. Let's just use general notation. No, maybe number notation. Round it out to 6, 7 decimal places. There we go. So you see it's the same number. Okay, so that p-value is small. It's definitely smaller than alpha, so we're going to reject the null hypothesis, which means we're saying there is evidence of a correlation. So we compare that p-value to our alpha value. P is low, so the null must go. We reject the null. The null hypothesis is that there is no correlation. When we reject the null, we're saying that there is sufficient evidence to support the claim of a linear correlation between a country's chocolate consumption and the number of Nobel laureates from that country. That is the same result that we got using the critical value method just a couple of videos back when we discussed that method. So that's how you use the p-value method. We need to use technology in order to find that p-value. But we see that using the p-value method here is really no different than it was when we were using the p-value method in the other sections. The only difference here is that when we compute our test statistic t, it involves that sample statistic r for the linear correlation coefficient this time.